So the Gram matrix is the matrix in which you have in which you measure the similarity between, I think we had called this capital K, where you measure the similarity between each of your observations and any other. And if you now think of making the RBF kernel extremely narrow, so very, very narrow, then you would just have ones along the diagonal and 0 everywhere else. And whenever you add a new observation, unless it coincides perfectly with one of the previous observations, you would add a new row to this diagonal matrix. And so we would get the identity matrix, and the identity matrix is the example of a full rank matrix. So an identity matrix always has full rank. And if you now start making your RBF kernel broader, then these entries here will start to become non-zero. They will grow a little bit. But even so, you retain this diagonal dominance. And so hence, whenever you add another point that does not coincide with another point, you create an extra dimension in this high-dimensional feature space. So, of course, the dimension that you embed to is never higher than the number of observations that you have. But as you keep adding more and more observations, you keep increasing the dimensionality. So this is where it comes from. Okay, then last week you heard the most important things about regression. And this week we're going to step into the altogether murkier waters of unsupervised learning. In particular, we will discuss density estimation and clustering. I call these waters murky because in supervised learning, you always have a training set and test set, and you can check how well your method does. In unsupervised learning, you typically, you don't have such reliable test information, and it is less clear which method performs better than another. And beauty often lies in the eye of the beholder in this field. So it's difficult to identify which method truly is best. Nevertheless, they are important building blocks for some other applications. And this is why today we look at density estimation and cluster analysis. So to start with a couple of applications, what you can do with density estimation, you can use it in classification. This would be called kernel density classification. And if you remember Bayes' theorem, what we did in linear and quadratic discriminant analysis is that we approximated these class-specific densities. So the probability of getting a sample at position X in feature space, given that we're looking at class Y, these class densities, we had approximated them using Gaussians. And well, a Gaussian is really the most primitive approximation that you could make to a class. And you can, of course, use any other density estimator in here. They will typically be much more flexible, give rise to more flexible decision boundaries. So you could say that this is a non-parametric classification technique. So you estimate those class densities. Then we can use it in non-parametric regression, and I'm going to do that in a bit more detail at the end of this hour. It is used in cluster analysis. We're also going to look at that today. And it is the conventional way of detecting outliers. So when we last met 2 weeks ago, we looked at the one-class support vector machine, but that is really a very new method to achieve that goal. So the conventional way would be to just have a collection of points that are known to be good in feature space, to estimate the density from those, and then at an arbitrary query point in feature space, ask if the density estimate at that point is above or below a certain threshold, and if it's below a threshold, you would call this an outlier. And then you can use it for similarity search and others. Now, there are 3 main ways to estimate densities, namely to use a histogram, or to perform a kernel density estimate, or to use parametric models like Gaussian mixture model. And we're going to look at all 3 today. Now, the histogram was the earliest of these. So you partition your space into bins. Typically, these bins are of equal size and equal shape, with a few exceptions in the literature. And you count the number of samples that fall into a particular bin. The problem that you can have with that is that you need to make an arbitrary decision, namely where to start counting. So I have an example here, a 1D example, a couple of observations, and we want to estimate the density of those observations. Then we first have to settle for how large a bin should be. You see that for very narrow bins, I can recover more of the more of the fine structure. But if the bins become too narrow, this estimate is going to be noisy, with most of the bins being empty or having just 1 or a few counts. On the other hand, if we make the bins wider, it somehow becomes more stable, but we also start to smooth over the fine detail. But secondly, once we've settled for bin width, we need to decide where we want to start counting. So here we have a bin that starts at -4, and here we have the first bin starting at -4.5. And both histograms were computed based on the same data, but they look rather different. So if you didn't see the original data, but just the histogram, you would probably think that, well, this is a unimodal distribution. You know, this would perhaps be acceptable as an outlier. If you look at that, you know, it strongly suggests that we really have 2 modes in the distribution. And as I said, the only difference was where the first bin started. Okay, so the histogram has a couple of issues, namely the dependence on the offset. Then if you look at data with more than 1 dimension, you also have a dependence on the rotation. So let's say if you decide to use square bins, you could arrange them, and if this is 2D feature space, you could arrange them like a Cartesian lattice, or you could arrange them at some angle. So you gain a couple of degrees of freedom, or there are a few choices you have to make as you go to higher dimensions. Then the result that you get is not differentiable. So you cannot use gradient ascent to find a local maximum in your density. And then I have mentioned the problem of the choice of bandwidth, but that is not intrinsic to histograms. We will have that same problem in kernel density estimation that we will discuss in a minute. Finally, in higher dimensions, there's the problem that you will often find sparse occupancy of your bins. So let's assume that we look at some correlated data. Perhaps the data was generated by let's say we have a 2D feature space here. And I'm drawing the isocontours of the true density, which I happen to know, which is a strongly correlated density. Okay. So if we now sample from this distribution and we try to approximate this density using histogram, we can now use a Cartesian grid. But we will find that we're going to waste many bins. So many of these bins will have 0 entries. And this problem becomes ever more dominant as you go to higher dimensions. So this is what I mean by sparse occupancy. Now to remedy at least this problem of the offset dependence, an average shifted histogram has been proposed, and we have discussed that briefly in the context of the pyramid matching kernel. This alleviates the offset dependence. And here the idea is simply that you compute multiple histograms, all of which have been shifted a little bit, and you then average over these histograms at a given query point. And if you now think of the effective impact that the kernel has, if I now have a bin this wide, and let's say I'm using not just a single histogram, but I'm using, let's say, 10 histograms to find this observation. Then at the location of the observation itself, I would find that observation in 10 out of the 10 histograms. So I would find it, if the bins are here, I would find it. If the bins are there, I would also find it. Okay, so if I now compute 10 histograms for these different shifted bins that I'm indicating with my fingers, you would find this observation, 10 times. If we now look at this point here, we would find it perhaps only in 5 out of the 10 histograms. See, because I'm starting with my bins here, and only now I start to see this observation, and now I no longer contribute this point. So we would perhaps get 5 observations, and at that point here, we would find it in just 1 of the histograms. And if you make this argument quantitative, you would see that in 1 dimension, you effectively start to weigh each observation with a triangular kernel. So the average shifted histogram at some location x then becomes an integral of your kernel. let's say, let's take another letter here. So what we start doing is we convolve our observations, which are here represented by Dirac peaks. We convolve these with, in one dimension, a triangular kernel. Okay, so the kernel would have just this shape here. So we could say this is and in higher dimensions, instead of the triangle, you would this kernel would be given by the autocorrelation of the histogram bin that you're using with itself. So we would now get a histogram that is still not differentiable, but at least you would get a density estimate that is continuous in the limit of using an infinite number of these shifted histograms. Now, that is an approximation that is sometimes useful, but perhaps you would want to have more freedom here in the choice of this kernel. And effectively, this is what you do in kernel density estimation. So in kernel density estimation, we estimate a density. I'm writing p hat to indicate this is an estimate. I normalize by the number of observations. We don't do that in histograms usually, because in histograms you want to know what is the absolute number of counts in a given bin, and it doesn't need to normalize to 1. But if we talk about densities, we like this to normalize to 1, so I'm normalizing here with 1 over n, the number of observations. Same formula as before, except for this normalization factor, and except that I've now included the parameter h explicitly. This is the bandwidth of our kernel. So this indicates how broad our kernel is, because it's a very important parameter. Okay, and this can be rewritten as a summation over kernels that are centered at the observations. And for this whole thing to be properly normalized, we require that the area under such a kernel be 1. So if we do this for the same data, there are two ways we can look at it. The formula on the top suggested that we have these Dirac spikes at the locations of our observations, and we smooth this train of Dirac peaks with some kernel function, or equivalently, you could say that we place a kernel function at each of the observations and add over all of them. So down here, I've indicated this particular kernel that I've used. I've centered one kernel on each of these observations. And now adding over all of these, I get this estimate that you see. Okay, so that would be your equivalent of the histogram that we've seen before. Again, the choice of the bandwidth clearly is important, but you see that this estimate now is much smoother, and it has inherited the smoothness from the smoothness of the kernels themselves. If you want the result to be strictly a density, you should also require that the kernel not only integrate to 1, but also be larger than 0 everywhere. But sometimes people use kernels that are partially negative to reduce bias. Sure.
Right. You put the kernel on every single observation, basically. Doesn't it kind of depend on the observations themselves, as in how they're separated?
It's a very good question. So I think you're asking if the shape of the kernel matters depending on what observation you put it on. And if we look again at this example, so we have some high density area with many observations, and here we would like the kernel to be pretty narrow so as to reveal the fine structure. But then we also have some isolated observations. And if we now use the same bandwidth everywhere, these isolated observations will give rise to, single peaks that are, alone in the middle of nowhere. And so given these observations here, just a single observation out there is not enough to make us believe that we have a local maximum in the density here. It more looks like this is a distribution with some tail, and there's of course a finite chance of getting observations out there. And I happen to have generated this data, so I know that this is in fact the truth. It's just a bimodal distribution, and there's some non-zero probability of having observations out there. So one should make the kernel width depend on the density, but the density is something we're trying to estimate. So that's why it's a little bit tricky. There are heuristic procedures that, for instance, ask how far the kth nearest neighbor is away, and then use that distance in the determination of the bandwidth. Was that the question? Yeah, okay. Just make sure I'm answering the right question. Okay. So in words, what you do in kernel density estimation is to place a kernel or a bump on each observation. And then sum over all of these. And we can look at, so if you look at this formula, it is clear that the density estimate inherits all its smoothness properties from the kernel. So let's say if you take a kernel that is smooth, but you truncate it, just because you want it to have finite support or to have computational savings or something like that, this truncation implies that in your estimated density, you will also have these tiny jumps. So it would no longer be differentiable everywhere if you did that. Okay, so it inherits all properties for good or for bad from the kernel. And we can look at two extreme cases just to understand the effect of the bandwidth. If we make the bandwidth very, very large, in the end, we would get a density estimate that just looks like the kernel itself. So it would hide all the internal structure in the data. If we make the bandwidth too small, we will just get a series of, or we'll get something that looks like a nail board. We'll just get a series of peaks. And somewhere in between is the reasonable bandwidth. Unfortunately, it's very, difficult to say what exactly is the best bandwidth. And also, unfortunately, it's harder to figure that out than to determine the parameters that we see in classification. So we can look at this in terms of a random function. So we can look at the statistics of kernel density estimation. It's sometimes abbreviated like that. So we will assume that the random variables are identically and independently distributed according to some unknown density p of x that we try to estimate. And we can then ask for the bias and the variance of this estimate. So I can ask for the expected density estimate, and I'm taking the expectation over the position of the first sample, and then over the position of the second sample, and so on, until the observation of the nth sample. And just inserting the definition of the kernel density estimate, I will abbreviate this by saying this expectation refers to all observations from the first to the nth. So we have the expectation of a summation, and we can rewrite this as a sum over the individual expectations. And because they are identically distributed, it is sufficient to, all these summands will be the same. So my summation was over a total of n samples. So I get a total of n such terms. And I can take as a representative, for instance, just the first sample. And using the definition of the expectation, so this is the expected density estimate, and we we see that the expected kernel density estimate is just a convolution of the true unknown density with this kernel. So if we want the expected density, to be identical to the true density, ideally we would like to have the Dirac distribution here. So we would make the kernel as narrow as possible. So if we want to minimize the expected difference between the true and the estimated density, we want a very narrow kernel, one that approximates the Dirac distribution. Because if we use so let's just to show you an example. Let's say that the true unknown density or perhaps this is some spectral process, and this would be the true unknown density P of x. And if we now draw many observations from this process, and use some normal kernel, we would get a density estimate that perhaps with a little bit of luck would look like that. But we're going to blur over this hole in the density. And to avoid such a blurring, we would like a kernel that is very narrow. But as your question indicated, if we use a kernel that is very narrow, we would use a different color. We would get a density estimate that simply consists of a lot of spikes, which is not a useful density estimate either. Okay, so the fact that we would get lots of spikes, we can express in terms of the variance. So the variance of this kernel density estimate if you remember this formula, if we want to compute the variance of some function, we can write this as the expectation of the function squared minus the squared expectation. And this term here we already know. So this was the bias, and that would be the squared bias. So we can look at the remaining term here. By again using the definition of the variance here, or the expectation. And this term we've seen before. So the integral now, the proper way that this is done in the literature is that all of this is Taylor expanded, and then you can neglect terms that if you make n large or h small will become tiny. But to look at this qualitatively, let's make a different assumption here. So we said that to minimize the bias, it would be beneficial to make the kernel as narrow as possible. No. So the expectation of any function is just that function. The integral of that function multiplied with probability density. So, this could be any function, and I would just copy that same function here. However, there is a summation missing. No, it's not, because as before, I used the fact that they all follow the same distribution. So you get a total, you get an n squared term here. Where? Yeah, it's n times the integral, and it's 1 over n squared and overall. I think this is right. Yeah. So I could have so we had so the variance, if I write this out, this is 1 over n, and this is now the variance referring to a lot of random variables. Something. And if I want to pull a constant out of the variance, I need to square it. So I would get 1 over n squared times the variance of x1 up to xn of a summation a lot. And that will give me a factor of n, which cancels with the n squared. So this is correct.
The line above should be squared. The first line.
Where the x goes from 1 to n.
No. No.
That is the formula. If you have the variance of variance,
Okay, should be squared here. Yes? Okay, good. We all agree. Okay, thanks. Okay. So I want to make a qualitative argument. As I said, the proper argument, you would do a Taylor expansion here. The qualitative argument I want to make is to say that we're going to make the bandwidth very narrow, so we can consider this true density to be locally constant. And secondly, I will argue that the kernel we're using is just the box kernel. So it will be 0 outside its support and a constant within. And if I do that, I can pull both. So this is a constant, that is a constant. So I could pull all of these out of the integral. And the integral would then go not from minus infinity to plus infinity, but over the support of my kernel. So if I do that, then I will get some constant, let me call this k squared, and another constant p minus k squared, p squared, and we know that the variance must be positive, so this approximation that I'm making, my argument will only work if I say that p is smaller than 1. And if that is so, then making the kernel narrower will, through the normalization, make my k higher, well, because the area should be the same, so that for very narrow kernels, overall, this variance will become larger. And this is, well, what you would expect. So in low density regions, when you use a very broad kernel, you will always find a little bit of density. But if you use a very narrow kernel, sometimes you find an observation here and sometimes not. So sometimes there will be a bump and sometimes not. And this is what would give rise to high variance. Okay, so we have, as in many instances, a case here of bias variance trade-off. And we want to find the one bandwidth that would make this mean squared error as small as possible. So the mean squared error I can rewrite by adding and subtracting something. Okay, and I think we've done this once before. So I can take the first term squared and this expectation will not do anything to that term on the inside. I'm not happy with my signs yet. So what do we have? Is there a hat too many in the equation 4? No, I don't think so. So this is A, and this is B, and I have this is A squared, and this is B squared, and that one would be A times B. So yeah, this expectation is not going to do anything to P of x because that is not even a random variable. This is just a true density. It's also not going to do anything to the expectation of P hat because the expectation has already been taken, so this is just a scalar number and the expectation cannot change it any longer. So I can let the expectation refer to just that part, and here I can repeat the same argument, so it's not going to do anything to this second half. So what remains in the end is that I have the expectation of P hat minus the expectation of P hat, so this whole thing here is 0. And what remains is this expectation I can also omit because it's not going to change anything inside the parentheses. So what we have down here is the squared bias. And what we have there is the definition of the variance. So the mean squared error is the sum of the variance and of the squared bias. And by choosing an appropriate bandwidth, I will be able to minimize this mean squared error. Now we have two major choices. One is the shape of the kernel, and I'm showing here a couple of typical kernels. The only one that's really bad is the box kernel. This one shown here. And the others shown here are a triangular kernel, a Gaussian kernel, a cosine kernel, Epernechnikov, and so on. According to these Taylor expansion arguments, the best possible kernel, the one with the highest efficiency, is the Epernechnikov, which is simply a truncated parabola. So this is shown here in red, I believe. So this is 0. Then we have a parabola, which is truncated to, again, become 0. So this will give you, so what's nice is that the kernel has a finite support. However, unfortunately, the density estimate will not be differentiable everywhere because you have this cusp in the first derivative at these locations. We have the discontinuity in the first derivative. And when you change the if I now go from one kernel to the other, this is using equivalent bandwidths, all on the same observation. The only density estimate that's really different is here the green line. That's the one obtained for the box kernel. All others are really very similar. So it does not matter very much what kernel shape you're using. More important is the question of the bandwidth. So again, here are the observations, and this is for small, medium, and large bandwidths. And actually, this here is the one that comes closest to the truth. I know because I generated the data. So this would be the true density, and down here would be a reasonable approximation to that. Now, how to find this bandwidth, that's a really, I would say, an unsolved question. So parameter choice in kernel density estimation. Optimum shape is the Epanechnikov kernel, simply a truncated parabola. Bad is the box kernel. And all others are okay. Most kernels that people use will have finite support, but in between will look somewhat smooth. So for instance, people have used the cosine and others. So that would be a typical kernel shape. Now, regarding bandwidth, there are rules of thumb that are not very good, I think. Then there are cross-validation type procedures. So what people do is the following. You compute the following. 1 over n times the sum of the log of the estimated density at your observation number xi, where this kernel density estimate has been obtained from all samples except the one that you're looking at. Okay, so this is p hat sub minus I to say that bumps have been only put on all other observations. And then you want to maximize this type of likelihood. One problem with this is that it's sensitive to the microstructure in your data. So let's assume that your data has been discretized, and I'm interested in the large-scale density estimation. So I want to know where I have few or lots of observations at the big scale. But if due to the discretization there are always more than one observations at a given point in feature space, then this criterion is going to give me kernels that are infinitely narrow. Because you see, if this is a count, if the lowest count that I observe, if I plot this as a histogram, if the lowest count is 2, then each observation can be explained by the other observation at that same location and this can lead to serious artifacts. So, and so you have to make sure that your data, and if it comes from a digital sensor, it may often have some discretization. So you must be aware that if you use this type of criterion, that you are sensitive to the microstructure. On the other hand, if you now have a single outlier, this criterion is going to make your kernel so large such that this outlier still gets a little bit of density. So unless you use an adaptive bandwidth, it's also sensitive to outliers. And I've mentioned one strategy to use adaptive bandwidths, but only heuristics are known for these. So finding the proper bandwidth, let's say it's an unsolved problem. Okay, let's have a break.